Right, folks. Welcome to Ivana's Inaugural. This is something we do when we promote new professors. And it's a genuine pleasure to be doing it in person again. This is the first in-person event we've had for probably 3 or 4 years. Yeah? And so it's going to be the first of a series, and I can't think of anyone better to lead off the series than Ivana. So, again, welcome friends, colleagues, and in particular Ivana's family to this. Just a little bit of housekeeping. There aren't any fire alarms planned, but if one goes off, there are exits. Please just follow people out of the exits. And after this event, so after 7 o'clock or so, there will be drinks and dinner, so after photos and what have you, so stick around. I've got to know Ivana really very well over her years here, and she's come up through the ranks at UCL. And not only is she an amazing researcher, and we'll hear a lot more about that, she's an amazing contributor to the department and beyond. Right? So Ivana has headed up Athena Swan activities, looking at gender diversity. She's been a leading light in that, pushing it forward, pushing us all to do better. She's made a real difference to the department in that. But more than that, she's always outward looking, right? Always looking for the next challenge and the next thing that she can change, and to great effect, right? So I'm going to hand over to Ivana. I'm going to stop talking. It is a pleasure to introduce Ivana. I've been in talks that she's given to school children, and they're amazingly accessible talks, brilliant talks that have enthused the next generation as well. And so with that, I'm really looking forward to this, Ivana. So over to Ivana.
Thank you so much. Thank you, Steve. So hello, everybody. Thank you all here for coming today. Amongst you, there are many of my colleagues, both academic and non-academic, my friends, my family. So this talk is really designed to appeal to everybody and for all of you to find small parts of it which you could identify with. I love to be an academic. I love my research. I love my teaching. I even love the dreaded admin. I just do my best to choose to do things that I feel passion for. I feel at home at the university. I feel like this is where I belong, and that is really something that defines me. And today I will tell you a little bit about the journey that I had to get here and to become an academic. So I will first take you some 2,300 kilometers from here to a little tiny town, Prijepolje in Serbia in South Europe, where I was born and where mathematics for me started. So being born in that little town of rivers and mountains in what used to be Yugoslavia was a child's idea of happiness. Wild bicycle chases, volleyball, skiing in the mountains, swimming in the rivers, libraries, movies, and discos. And my parents were in the center of it all, always there, full of love and endless granite support. So from very early on, I was 10 or so, I became very interested in mathematics. So I was really interested in many other things as well. So I was winning competitions in essays writing, languages, chemistry, and physics. However, mathematics was very special to me, and with its language of symbols and shapes, which in itself was kind of independent and complete and beautiful, it just spoke to me. So also, I kept winning competitions in mathematics, and that led me to many different journeys around the country. I was traveling, meeting new people, went to many different summer camps, and that all together meant I was having a lot of fun, and my world beyond that little town where I was born was expanding. So a very big part of that journey for me was my hero dad, who used to practice mathematics with me, and also my teachers. My teachers were absolutely amazing. They were incredibly supportive, and they enveloped me with their warmth. They used to travel to competitions with me and prepare me, and I'm very grateful to them and to that school, which I really, really loved. So from that moment onwards, I really fell in love with the school, with education, and in the future, I always tended to connect with my teachers, the place where I am, with the institution itself, and to one day become a teacher myself. So my work and achievements also led to me being awarded a very coveted prize of being a child of a generation of my school. And this pretty embarrassing photo of me hung on the wall of the school for 1 year after I was gone, making my younger siblings pretend that they don't know me. So the world that mathematics opened for me kind of was beyond the physical borders of the little town where I was born and connected me with other mathematicians around the country. And the center of it all was in Belgrade, where there was this very special school called Mathematical Gymnasium, which was ranked #1 in the International Science Olympiads by the number of medals won by its students, like over 400. So with a suitcase in one hand and my dad and mom in the other, I traveled 400 kilometers north to Belgrade when I was 14, and then became part of that school. So the school was really unique and had a unique curriculum. Mathematics was split into 5 different topics: trigonometry, algebra, calculus, and I really loved them all. However, the first month in the first test in computer science, I failed. I actually got 0%. And at the time, I had a Commodore 64 computer, which I mainly used for gaming, and unfortunately did not learn any algorithms. So Belgrade was really fun. It was exciting. I was like learning on my feet, becoming independent, and I just developed my love for music, bridge, and I had my first jeans ever. However, I really had to up my game. And this time, I wasn't the best. There were people around me who were much cleverer and who were much better and had better knowledge than me. So I really had to up my game. At times, I felt like a little piglet flying in the sky and surrounded with all others who just looked like birds who knew what they were doing. And so I decided to grow really big, big wings. So I upped from my Commodore 64 to Pentium 126, surrounded myself with books, and started really to learn my algorithms and started. I also continued playing computer games. And my favorite game of all time, Heroes of Might and Magic, which I started playing around that time, I play to this day, as my children well know. So if you're ever wondering on a Saturday afternoon at 4 p.m. what I'm doing, that is what I'm doing. So computer science at that time became an integral part of my life. So a natural move for me after I finished my high school was to actually enroll into the undergraduate degree in mathematics at the University of Belgrade, which was just kind of around the corner. And at that university, the professors were already some of which I knew from my school. And I also knew quite a few students because many of the children from my school went to the same university. So I felt very much at home there and really had a really great start. However, the period at university also, had its own crazy stories, and there were lots of ups and downs. So for all the students out here, because I'm not going to go into details of that, but if anybody is interested to hear what all the ups and downs in the university can be, because I had my share of failures there and wins, please do ask me later, maybe over drinks. But maybe the most defining things at the university of that time is that I was a student in the time of political turmoil in my country. So in the 1996, there were massive protests against the then president Milosevic, which a student protest, which I was part of. And for 6 months in the streets, I was actually preparing geometry, an exam from geometry. And that was actually my favorite subject, and because I really loved Euclidean and the Lobachevsky geometry, and I loved how both combined, they could describe the universe. However, the world around me was just getting more and more crazy. In 1999, Belgrade was bombed, and this happened during the last and final exam at the university. I was preparing topology in the bunker underneath our building for 3 months. And when I took the exam, on the wall of the examination theater, it says, in case of a bomb or a siren, it is allowed to leave exam room and go to the nearest bunker. So these were really extraordinary times, and I think what I learned in those times is to really not take life for granted and not to sweat small stuff. My final exam and the war were kind of coincided and they ended in the same time. And then it was time for a new chapter, both for my country, but also for myself. So I traveled to Oxford to start my new degree. And this is a degree in applied mathematics. Because you see, I've been doing theoretical mathematics for many years. And I really wanted to do some applications in the real world. And the degree that I chose to go to, which was the Master's in Mathematical Modeling and Scientific Computing, was one of the best world-renowned degrees in this area. So it just seemed the most natural thing to do. But I was really, really thrilled. I was thrilled to be accepted to go to Oxford, and absolutely loved and was so excited with just the first sight of it. In the first month, while we were choosing our projects and which projects we would choose for as a final one, although originally I thought that I might go into finance, which was not surprising given the economical crisis that we just went through. But in that theater, as all the professors were coming in and they were talking and presenting their projects, one of the professors, Professor Andrew Fowler, came and he showed this on the screen. And I was just such a young student, and I was looking at this, and I just thought, this is where my heart is. And just pure gut, I decided to go in the direction of medicine and to do some applications of mathematics in medicine. So my first application was the mathematical modeling of leukemia. So in particularly, I was interested in the chronic myelogenous leukemia, which is characterized by this chromosomal change in the cells, which cause cells to proliferate fast and wide, the abnormal cells, and then until they can totally obstruct and perturb the way the blood system works. What really interested mathematicians, though, was this very particular behavior of these abnormal cells, which was kind of can be represented with these oscillations. So one more person joined our team that year, and that was a professor, Michael Mackey, a famous professor in mathematical physiology from McGill, whose model actually is called Mackey model, and we were using that model to model the behavior of the normal cells. So in my master's, I combined the normal cells and the abnormal cells into one model using his as a start. And then I try to model how the blood cells are actually behaving in leukemia. I used some classical applied mathematics approaches and did some very deep kind of phase plate analysis in steady states. And I predicted that, the model predicted that this very particular oscillatory behavior of cells that we see in the blood. And that was really exciting to me, to actually be able, with mathematics and simulations, reproduce something that is happening in the real world. So the simulations and mathematics and computational modeling really became an interesting way of seeing the world. So my results were resulted in actually 2 publications with the professors Mackey and Fowler. And actually only now I realized that that was probably quite special. I also that year met my best friend for life, Christina, with whom we were working together on delivering our final MSc thesis. And as it happens, on the last night before having to hand in the morning in the examination hall, she was writing the final 2 paragraphs of it. And while we were rushing, and as the printer was broken down, everything was going as it shouldn't be. So we managed to get there in the examination hall literally 5 minutes before the end and the submission. So to all the students out there, it happens to everybody. Don't worry. If you're not the only one who does things in the last moment and who's like, that is just a common practice. So after my master's, I got some offers actually from industry. However, I rejected them because I really wanted to do a DPhil. And since I was an overseas student, only overseas students here know how actually challenging that is when you're looking for a DPhil and you are an overseas student. However, I was very lucky and to know Professor David Gavagan, who thought the best of me and who knew that in FMRIB there was one place, an empty place for a PhD student. So he took me with him to a meeting with Steve Smith. So the meeting didn't last very long. We were both very excited. And very soon, Steve just said, so see you in September. The world went yellow and pink in the same time. So I became a PhD student at FMRIB. FMRIB was at the time a young lab that was studying and was working towards to becoming one of the best labs in the world for neuroimaging. Neuroimaging in itself is this fascinating science which is trying to look inside the brain and trying to measure function and the structure, trying to understand how the brain works. So traditionally, when I say we want to look inside the brain and see how the brain looks, we will probably want to open up the brain and then look into some tissue and put it under the microscope. But obviously, we can't do that with living humans. So the neuroimaging is a special science which actually looks at the magnetic resonance imaging, which, and then derives conclusions from there. So magnetic resonance imaging, or as we call it, the MRI, is a standard procedure that uses magnetic fields and radio waves to create this contrast that we see here in the brain, so we can non-invasively see what's happening inside the brain. In particular, there is a branch of the MRI called functional MRI, which is actually in a series of these MRI images extracting and can see how these different areas of the brain function as we are doing certain actions. For example, as I'm speaking right now, or as I'm looking at the light, probably some areas in the back of my brain, in the visual cortex, are actually firing, and they are creating those kind of little red mapped areas that we can then study, and we can then study how the brain behaves in different situations. So what is then the problem? What is the problem in functional MRI? So functional MRI is, to be possible to do it, we need to do a very rapid sequence of the MRI images. So we need to use a sequence called echoplanar imaging sequence, which we call EPI. And that sequence is very susceptible to artifacts, to all kinds of problems that can happen. So for example, on the top there, you can see some very strange looking images, and those kind of artifacts happen. They're called susceptibility artifacts. And they happen because in our brain, we have tissue and air next to each other, which have very different magnetic properties, and hence that creates a signal loss that we can then see in our images. At the bottom there, you can see a consequence, for example, of motion artifact, because the subjects need to lie in the scanner for extended periods of time, and very often, especially in children or in old people, there will be some movements. And so the MRI image will be capturing that movement, but that in itself as well corrupts the analysis. So my idea field really was to look at these kind of problems and see how we can solve these problems. So when I started, I had 3 different supervisors, and I was between 2 different labs. So with one foot, I was in the Department of Computer Science, and my supervisors were Professors David Gavagan and Professor Andrew Sully. And on the other side, I was supervised by Professor Mark Jenkinson in FEMRIB, who was absolutely brilliant, who was extremely supportive, intelligent, and I was so lucky to be his student. So my project really started with me trying to create a simulated version of an MRI scanner. So an MRI scanner is a big machine that creates these MRI images. You see, MRI scanner is full of different coils, which are all producing different kinds of magnetic fields. It also, you can see there's a person inside these coils. So my task was to actually create a simulated version of this and to create simulated images. So I started developing my model using already some existing theories and equations. So Bloch equations to model the behavior of the magnetization in the brain, Maxwell's equations to model the behavior of the magnetic field around the brain, then the equations to model the rigid body motion of the brain. And then I was using a range of different techniques, from discrete event simulations, perturbation methods, finite element methods, taking into account the complexity of the system and the complex temporal evolution of the system in time, following the object and solving it in the object reference frame. So this is the first prototype of the solution that I created. The simulator is called POSSUM, and it stands for the POSSUM. It stands for the physics-oriented simulated scanner for understanding MRI. As you can see in FEMRIB, we were really, really keen on our acronyms. So the POSSUM could take any simulated object, simulated brain, together with a path sequence and a motion sequence that we would like to exhibit. And then in this, the black box, the machine that I created, we come up with the signal and the image itself. So here you can see some of the results that I had from some of the early results. So this is an EPI scan with no artifacts. And you can see these beautiful, perfect-looking images that we can create with a simulator. And now these are the actual artifacts. So simulator was managing very faithfully to reproduce all the really significant and complex artifacts that were present in these images. So chemical shift, eddy currents, ghosting, motion, B0 and homogeneity. So this is the one I mentioned earlier, the susceptibility artifact. And you can see in the top 2 rows are the simulated images, and at the bottom is the real data. So the real data really extremely well matches the simulated data with B0 artifact. And what's the beauty of the simulations and why they are so interesting and useful to use is that we can switch this artifact on or off, which is not possible in reality. So in true experiments, we can never do that. Hence, with simulations, and we can actually develop and improve the tools for correction of images. Finally, when all combined together, all the different artifacts and the motion, I was able to predict a range of different fMRI sequences. And for example, here, this motion is correlated with the experimental paradigm, which creates in the images themselves some erroneous activations, which could potentially lead the experimenters to make wrong conclusions about the neuroscience and create wrong understandings. So POSSUM, so it took 3 major revisions and 30 densely packed pages. That was my first publication in this area. Now looking back, I think probably I should have split it into more. But at the time, I was just trying to put everything together and to create a story. the POSSUM itself became part of the FSL software, which was at the time becoming one of the top neuroimaging softwares in the world. This opened up a whole other range of possibilities. So first I want to thank Saad for actually creating this beautiful slide, which as this event actually coincided with the 25 years of FMRIB, for which this slide was originally prepared for. But I'm really proud to be part of that history of FSL and part of that team that was creating FSL. As a group, we had such amazing opportunities, and we went around the world to deliver courses in FSL and train new computer scientists and neuroscientists how to use it. And that for a PhD, for a young PhD student like I was just an immense, brilliant experience. And it was just truly a dream PhD. In addition to doing the research and spending lots of time in my lab, and thank you, Steve, for all the amazing weekend lunches we had at the newly built floor of FMRIB, I also was very interested in other things around Oxford. So I was part of every party and every common room discussion and broke into quite a few balls. But I was an extremely keen sports person. I was a captain of the Oxford University Volleyball Club for years. I was also a keen rower, rowing for my college. And I was a skier going for abuser competitions for Oxford. So all of this created that feeling of balance in me, which again, I really always advise my students to create that in their life. So the POSSUM, after I finished my PhD, I did move on to do other types of research, but I still work on POSSUM. So when I was already at UCL, I was very lucky that my colleague and friend, Gary Zhang, was interested in it too. And then with his PhD student, Mark Graham, we developed this diffusion MRI extension of POSSUM. Jesper Andersson then joined our team. Jesper, who is at FMRIB and who was developing the EDDI and EDDI correct, the tools in FMRIB, in FSL for correction of artifacts. So with him, we did some really great work on correcting for the within volume movement, on correcting on motion with susceptibility interaction artifacts, and the FSL tools that for correcting artifacts were improved as a result, and they were used for a range of different studies around the world, from Connectum, UK Biobank, and the baby Connectum in particular, where the motion is very common. But back to where in timeline, when I finished my PhD, it was really a time of celebrations. So after I graduated in Radcliffe Camera, I also got married to Richard, the love of my life, who was then a young and aspiring barrister who just got a position in London. So it was time to move and to come to London. So while I was looking for where to go in London, which university to go to, a very good friend whom we spent many good journeys going London-Oxford trip, Tim Behrens, advised me to come to the lab of Danny Alexander, as he said that he's a really great guy. So on this advice, I came and applied for a position in Danny's group. Danny was at the time starting a new group on microstructure imaging of the brain, and that became part of my postdoc. So microstructure imaging was then quite a new thing for me. So we are still in the MRI area. However, we were now using diffusion MRI, and diffusion MRI is an area of MRI that uses is sensitive to the movement and a random movement of the water molecules and the brain, which are themselves sensitive to the restrictions in the brain. So, for example, in the brain, we have these very long fibers that are connecting different parts of our brain. These fibers that are like long and large, like motorways in the brain, in those fibers, the dispersion of these water molecules takes these very special, kind of almost cylindrical-like shapes. And using special techniques in microstructure imaging, we can actually learn what are the properties of this shape, and from there infer about the properties of the tissue itself. So, for example, I was very interested in looking at the axon diameter and trying to estimate what is the diameter of these fibers, and also what is the density of these fibers. So now why was this important? It's because in disease, these axon diameters and the axonal density change. So, for example, in diseases like Parkinson's or any kind of neurodegenerative diseases, those characteristics are starting to change. And if we can measure them using this non-invasive way of imaging, we can actually then predict what will happen to different patients, and we can diagnose them for future treatment. So, but in order for this to work, because we are talking about such subtle, small things in our brain, so axon diameter is probably on the range of 1 or 2 microns. This is really small. So for that to be visible in those MRI images that you see, we needed really, really powerful tools for analyzing the images, but also we needed extremely powerful tools to acquire the images themselves. So this is one of the standard sequences for diffusion MRI that was used at the time, called the PGSE. So sequence, this pulse sequence to an MRI scanner is the same as a sheet, a music sheet to a piano. So by creating these different, by all of these different symbols actually have different meanings, and as maybe some of you know, in an MRI scanner, when you hear all these different sounds, it just means that all of these different things are being played out. So when I arrived and I started my postdoc, Danny thought that maybe that sequence wasn't good enough. Maybe we can do better and create a better sequence. And this is how I started. That was my postdoc questions. What waveforms, what sequence should we have so that we can maximize the way we can image and we can really truly see the axon diameters in the brain? So I started by actually discretizing this sequence, allowing it to be anything it wants to be. And then I used some very sophisticated matrix method computations that were originally created by Professor Paul Callahan. And then I implemented them, then upped them into the three-dimensional space, and then used them in this very large experiment design optimization way, where for a given tissue model and for a given pulse sequence model, we can calculate the signal, and then from it, look at the objective function and try to, by minimizing this objective function, try to increase the precision on these axon diameter estimates. So in a way, it looked a little bit like this. So it's, in this experiment design optimization, we would start with some initial point where the sequences could just be this random dots, as you can see there on the left. But then through an iterative process, while we are trying to minimize the objective function, we would get the optimal waveforms. And these optimal waveforms, the first time I got them, when I was trying to actually optimize the waveforms to be able to image something as small as half a micron in diameter, I got this really cool, interesting looking kind of waveforms. You see, first one of them is kind of showing these oscillations. As I started increasing the size of these axon diameters, these waveforms started lowering in the frequency. And it kind of almost felt as if the scanner and the brain were kind of talking to each other. And that as we went and increased the size of the axons we are trying to image, the scanner was preferring these kind of low frequency oscillating waveforms. So these results were so exciting, and so they had to be really thoroughly validated, which I did both in simulation and experimentally, together with Bernard Xiao on the scanner and some really cool-looking phantoms. Also, in order for this to be computationally feasible, the sequence had to be parameterized. So I then chose between many different waveforms until I settled at a trapezoidal waveform, which was to become the one to use in the future. However, the time was running. My postdoc was supposed to run out. I was about to publish 6 different papers, and all of this work was supposed to be published. I was applying for a fellowship, and I was looking for a permanent lectureship position, all in a span of 2 years. And I was pregnant with a baby. So, with a baby. So I really had to sit down, and I put this image here you see on the right of climbing the Mount Everest, and then created a very strict timeline of all the papers and all the fellowships and the ideas, the collaborations, everything that needs to be planned out. And then with my head down, I was just going from base camp to base camp. And I think I've so mastered this graph that I would probably be able to go to Mount Everest and climb it right now, because I would know it by heart. So I was very lucky that I did indeed publish all those papers, and I did indeed was awarded a Livercombe Trust Fellowship, and I did indeed get a permanent lectureship at UCL. And then it was time to just go and have my maternity leave of 6 months. Little did I know, nobody told me what it's going to be like. I mean, I seriously believe that the humanity must have kept this as a big secret, otherwise nobody would have babies. It was pain, multiple hospitalizations, as my husband will know, who spent many of the nights on the hospital floor. No sleep, and trying to work in parallel on just a little bit of research to finish that paper up. But we were so happy. We were so happy. We have a baby. When I was back to the lab, the things were already moved on a little bit. So in the first 7 days when I was back in the lab, I managed to do all the work that I was trying to do in those 6 months' time. So to all the new moms out there, never try to do any research during your maternity leaves. It is really not productive. So also, the work at work was so much easier than the leave at home. It was also a really interesting insight, because finally you could sit down, have a coffee, and have a think, and have your brain for yourself. But it was still challenging. It took a few months before all the baby was settled, and before I could really feel myself again. But I was really, really lucky, because in the lab at that time, a new PhD student had started, Andrada Janusz, who was just brilliant, clever, and hardworking, and I became part of her supervisory team. So she has already, while I was on the leave, started a GPD approximation of those trapezoidal waveforms. So she has already done that, and that allowed us then together to create a whole software package, which is called MIST. And this is a microstructure imaging sequence simulation toolbox, which for any given gradient waveform and for any tissue model that simulates the tissue in the brain can calculate a diffusion signal. So at the time when this was finished, it was already time for my second maternity leave, this time with twins. And so here we go again, the pain, the multiple hospitalizations. But I was really, really wiser by now, and I learned my lessons. I did indeed breastfeed in that particular way to manage to feed my 2 little growing babies. But I also got a much longer leave from work. I had much more house help. I made sure I get better sleep. Decided not to do any research, but I did do the meetings. with my students who used to come to the house, and while they were like looking and shuffling my little babies, we were having our meetings, and that was a lot of fun. It is possible to do meetings in the maternity leave. So now so when I was back to the lab, again, the things have moved on. As all new mothers know, when we come back from maternity leaves, the research moves on, nobody waits, and that is as things should be. But what is important to do at that time is to jump in and see what can I do next. So what happened to me when I came back, there was a new postdoc in the lab called Enrique Caden, who actually did some things of his own and looked at the sensitivity of the signal in terms of axon diameter. And he actually found that the fat pulses, the kind of PGSE increases the resolution power axon diameters. And that seemed a bit conflicting to my previous optimization results. So that meant that I had to go back to the drawing board. I was very confused. So I did a lot of different simulations, and I did lots of different types of work with Andrada, and we were trying to figure out what is happening. So we went really back to the basics and just stripped it down, and instead of looking at the big complex optimization systems, we were just looking at the signal, diffusion MRI signal, and how it changes in terms of the axon diameter. When the axon diameter changes, how much does that actually affect the signal? We were a really great team. So me, Andrada, Gary, Dani, and Enrique, and we kind of all together started working on this problem. And we found that, indeed, all the conclusions we had so far were correct. However, we were estimating diameter and diffusivity simultaneously. So, however, when we switch off that diffusivity and we only look at the axon diameter, we do indeed see that the PGSE is the best sequence and the most sensitive to axon diameter. However, this whole research led to completely new and novel findings. This was only the case if the gradient waveforms, so those gradients in the magnetic field, they were perpendicular, perfectly perpendicular to the fibers themselves. However, even at the slightest angle difference, for example, just 2 degrees off between the gradients and the fibers, and then the OGSE was winning. And that was because the B value, which is the way to almost characterize the power in the scanner, was so massive for these PGSE sequences. It was just simply killing the signal, and hence the OGSE was just the sequence to do. This was also the case for dispersion, which both are really present in the brain, as most of the fibers are never perfectly parallel, never perfectly aligned. Another discovery that we made was we found smallest identifiable diameters for a range of different scanners. And actually, there were quite some dire results, because what we found is that on a standard, typical clinical scanners, we can only see axon diameters of 6 microns and more. And those were really quite large. There's less than 1% of those kind of diameters in the brain. And we really needed very strong gradients, like those of 300 millitesla per meter, to image something that is as small as 2 microns. And those kind of gradients and those kind of scanners were really not available to general population, and they were only available in very special laboratories. So all these results were confirmed analytically as well. So I worked with Marcus Nielsen on then creating analytical expressions for the connection in this, between the axon diameters and the gradient strength. And it's really cool, the work Marcus did, where we can, like, just in 5 seconds, scientists can now look at the equation and find out from the equation whether their scanner can actually visualize those sizes of axon diameters or not. The results were also validated experimentally by my PhD student, Libina Sresha, who, using a range of different experiments, some on microcapillaries, on clinical scanners, and some on a sciatic nerve of a rat. Like in this situation here, we see these images of a nerve. She's shown that the RGSC sequences, our optimized RGSC sequences, were estimating axon diameter and density extremely well, and they were doing much better than the standard PGSC. However, and this was all really great and cool and produced lots of paper, but it was also quite harsh because it kind of showed that we can't easily image these axon diameters using the standard clinical scanners, and that kind of made me question what to do next. So this was until I then went to a conference sometime in 2019, and I met there Flavio Dell'Acqua, who presented this work where he totally changed kind of the approach of looking at the axon diameter. So he completely ignored the small diameters and was only focusing on the large ones, and was just he created, he was also not estimating the axon diameters using standard fitting methods, but he would use just two different diffusion MRI sequences, create a signal from those two, and then subtract the two signals, and then the remaining signal, which we call here the TDR contrast, was the one that was only sensitive to those axon diameters. And as we can see, that, for example, from 6 onwards, we can actually see quite large TDR. And then he shows some really cool results in the brain as well. So we joined together, and with my experience in optimization, I have, with my PhD student, Will Warner, and Andrada, and Marco Palumbo, we sat down and we optimized these sequences and created some really good contrasts and really almost a new way of imaging called temporal diffusion ratio, the TDR, which we then validated also preclinically on the spinal cord of the rat. So this was just actually published this year, so it's quite a new work. What I also started dabbling in was using machine learning to estimate axon permeability. So with Dani and Gemma, who kind of started that work on estimating, looking at axon permeability using machine learning, I then extended that work with my PhD student, Ioana Oprea, and with Marco Palumbo, and we looked at the cuprison-affected mice, and we found which actually lose myelin in some of their axons in the brain, and we found really that the permeability increases in these situations, and that machine learning was creating this incredible results. We were actually the first lab in the world to use machine learning to estimate this, and the machine learning from then on became such a big thing and kind of almost revolutionized the research for many of us. It was my first time to actually use it. I have never had any experience with it from before, but I just had a feeling that machine learning was here to stay for me as well. In parallel, I was really involved in the life of the department, like Steve says. There was a very big part of my life and very big part of my heart. So especially I was involved in the equality and diversity strategy. So drawing from my own experience and the challenges I had and those of the women around me, I've found that actually going on this pathway from becoming a student to becoming a professor does have challenges for many. So I looked at the actual data in our department, and I found that for women, so we have from the undergraduate students to postdoctoral level, on average we had 23% women. However, from the point of becoming an assistant professor and more, that number, that percentage was rapidly dropping to 11%. So we had a classic case of a leaky pipeline, which was happening kind of around this age between 28 and 40, when women are starting their family, trying to establish the work-life balance. And many of them feel that in academia, they don't have a perspective of the stability, and in many times, even the atmosphere itself. So what we have done as a team, we created this supported transition for women in that period. We expanded on a scheme called Proleptic Lectureship Scheme, in which when a fellowship is awarded, we can then create opportunities for women in our department, women and for men. we created stronger childcare support, network support, and all of these different actions led to a steady increase of the percentage of the female faculty. So from 11% in 2010 to 21% in 2018. It was a 10% increase. This was 8% more than the Russell Group university's average. And now, this is the data from 2010, and this is the data from 2018. And we felt that we are extremely close and that we have closed that leaky pipeline. Of course, I haven't done this by myself. We had the most amazing, dedicated committee, far too big for me to name all of them. But I will just mention that one of the members from that committee, because she's just right here, Caroline Wardle, Professor Caroline Wardle, was one of the most instrumental people who came to our department around that time, and she was just instrumental in helping us set all of this up. What we also had as a department, this was essential, were the dedicated, personally invested leaders. At time, we had, at all of our meetings, the head of the department sit with us. At times there were two, because Steve, even before he was head of the department, he was sitting with us in these meetings with the previous head of the department, who was the John Shaw Taylor. So with them and with our deputy heads of departments, Professor Yvonne Rogers, Danny Alexander, and our senior female professors, like Professor Anne Blandford and Lourdes, it was just essential for that, to have that kind of support for these schemes to succeed. We got multiple awards for this. We got bronze award from Athena Swan and then silver. We were one of only 3 UK's computer science departments to get silver back in 2015. We also got 2 Minerva awards from the informatics from Europe. After all this, it was time to take a sabbatical, I thought. I've done a lot of things and research, everything was going well. But it was time to have just step back and take a breather and just assess where I am with my research. At that point, it was a slightly different situation. I was now associate professor, much more established, more stable, and my little kids were not that little anymore. They were bigger, so I had more time and more flexibility to do more things. During all of this time, as my number of responsibilities was increasing, I had to find many different ways to keep up and to be able to be on top of it all. To be able to apply for fellowships and get professorship and have little kids and be in the home, be everything. I had to be a version 1, version 2, version 3. And to do all that, I read many, many, many books. Some of the favorite books that I have are here on this slide. So for any of you who are interested, you can, we can talk about it later. They really affected me. In some of them, for example, The Brain, The Story of You by Professor David Eagleman, really made me think about emotions and how emotions affect our decision-making. The book on The Body Keeps the Score, or When the Body Says No, also taught me how it is essential to look after our body and how, although you have all this energy in your mind, you have to look after everything for you to be able to succeed in the way and enjoy life to the full. So, oh yes, and here is the Hate Me Now, Thank Me Later book that I particularly read so that I can see how to be a better mother. So that really led to some transformational changes in me as well. So I used to be one of those students and one of those people who spend all nights working and checking emails whenever and weekends. And that was, don't get me wrong, I absolutely loved it and I wouldn't change it. I was doing it because I just really liked it. However, that can take a toll on you and in your body. And as you have more responsibilities, it just becomes more and more challenging. So I became a keen yoga practitioner. I run most days in the week. I eat very healthy. And I really prioritize my sleep. And on every Friday morning, if you wonder where I am, 9 a.m., I'm probably having a massage. So that was really essential and important to do. So during the sabbatical years, lots of different thoughts, and in years that were coming to it, lots of different thoughts were going through my head. And, you know, things about, in general, humans, about, you know, with our caveman mind and emotions, and how the decision-making is often impaired, and I was thinking about AI. I didn't even know where all of this is going. But I kept thinking, you know, this was also the times of Brexit and really kind of big political changes, and I just kept thinking, how can, you know, human beings being helped, and what can I do? I also felt a little bit saturated in terms of my imaging, and I really wanted to expand and look at other types of data and look at other types of applications. I felt the need to make a more concrete impact, and also a need to enrich my simulation worlds with some kind of realistic and real worlds. So it was time for a change for me. So I went into an office of a uro-oncology surgeon, Professor John Kelly, and I just said, hi, I'm Ivana, and I'm a mathematician and a computer scientist. Is there something I can help you with? And that was the beginning of a really beautiful friendship. So Professor Kelly told me how after major surgeries, while the patients are recovering in the hospitals, they spend days just being looked after monitors and doctors and nurses. However, when they are then released at home, they are totally alone, and there is nobody looking after them. So the readmissions and complications in that period are really common. So up to 30% of the patients are then readmitted in the 30 days after major surgery. And the two main causes are infection and failure to thrive. And really, if we were able to detect some of these complications early on while the patients are at home, we will be able to provide the right treatment sooner and to reduce the readmissions. So we set on to create a new digital platform to do the remote patient monitoring called HaloX, where the patient collects, wears a sensor that we designed, it collects the vital signs. Then the data is sent to the app, the patient self-reports, and the data is securely transferred to the GDPR compliant server. The data is analyzed and combined with other types of data using AI techniques. And then the results are sent to the clinical team, which then, if the symptoms are alarming, the patient can then be directed to a GP or hospital. So some of this work was already done when by Professor Kelly and his PhD student, Dr. Pramit Ketrapal, and they were already looking at how they could be following the vital signs of patients from home, and the results are very promising. And when we looked at some of the data that we were getting, we could very clearly, even visually, see the big differences between the patient behavior in well patients and the patient behavior in those patients that will ultimately be readmitted. And sometimes the sign of troubles were very brief, and it would happen just 2 or 3 days before the readmissions. So it would give plenty of time for something to happen. So creating HaloX was challenging and still is challenging. So we created a patient portal with wearable sensors, a home sensor, the clinician portal, the NHS portal, the connecting it all to, trying to connect it all with Epic, and also trying to create data aggregation platforms combining the genomics, the imaging data, the hospital data, and the data that's collected at home. So this was the vision, and lots of these parts of this vision are actually, some of them are completed, some of them are in process, and some of them are to be fulfilled. So in my team, we started gathering a team, and for the back-end architecture that was primarily had to be developed, my postdoc at the time, Ronnie Stafford, he was the tech lead, and he really pushed things forward. We were looking into wearable sensors and looking at the heart rate and movement and designing, and my PhD student who started with me at the time, Mike, was looking into those, choosing them, and Tiara, a medical student, she was looking into validate those and show that what we are getting is sound. We've also developed an app that can be used by patients and with which patients could use the clinically validated tests and surveys with which we could be following them, and they could be reporting their symptoms. Once we designed the first prototype of the platform was to be clinically tested. So we had, this is a clinical study called HALO-S, and it is still running, and so far has over 60 patients are recruited from the UCLH hospitals. And on this study, we are collecting biometric data from wearable sensors, and we are looking at the quality of recovery assessed through the use of prompts. So this study wouldn't have happened if we didn't have such close link with our clinical team. So Huriye Kotsadag is extremely are hardworking and charismatic clinical design, and she is instrumental in actually making things happen on the ground. So in recruitment of the patients themselves, of giving them the sensors and doing all those kind of things that were really important, but us as just computer scientists would not be able to do. We've also got approved the UCLH transformation project in which we're introducing TWOC at home outpatient service. So TWOC is a process by which post-prostatectomy patients need to remove their catheters. And we have probably around 800 of these performed every year. So using our system and our platform, it is much easier for the patients to do that now from home. And we are now we finished the initial pilot, completed with success, in which 16 patients successfully performed this self-TWOC remotely with no reported complications, and said that they would 100% would recommend the service. So this is really important for us, these steps, because these are the steps of making an actual impact in the hospital itself, and they are necessary for things to move on. In parallel, my team of computer science PhD students, again, together with clinicians, so here, Mike and Professor Steve Harris, we are looking at, can this remote patient monitoring data improve the prediction of unplanned readmissions after surgery? So we are looking at the predictions that are just based on their hospital data, such as age and biometrics, but we are also looking at to what degree the wearable data improves the predictions, and we find that the results remarkable. My another PhD student, Adamos, together with Zaftan Agdu, clinician, they are predicting recovery of continence at 3 months in men following this type of surgery. So at 3 months, when we know how many pads, for example, the men are using, and we know their age and comorbidities, and together combined with this remote patient monitoring framework, we can actually predict which of these men at 12 months will be continent or not. And then depending on that, we can tailor how we could help the men improve the prospect of their continence. So this is a clinical tool that we are building in which the clinician can actually just put in the data from patients, and then in this there is an AI algorithm that analyzes the data and makes the prediction for the clinician, that then clinician will know for each different patient what are their outcomes and what are their prospects in terms of their continence at 12 months. One of the key features that we are using in the AI algorithm that I just showed is actually the urethral length. And this membranous urethral length is currently being calculated by a clinician just looking at the image and then putting the 2 dots on it, and then looking at the distance, and that is really not, because of the difficulties of acquiring, that's not really used as much in the clinical world. So what we have done, what we are working on with one of our students, Kelly Hong, is we are looking at automated measurement of the membranous urethral length using MRI images and using deep learning. So you can see here in the middle is the ground truth, where in the middle column, where the clinician themselves was actually segmented, this urethral length. And then on the right-hand side, you can see the algorithm prediction that was trained on the clinical data. We're also looking at prediction of morbidity in patients with urosepsis with my PhD student, Ivana Drobnjak. So we looked at the sequential organ failure, like SOFA scores, which are used standardly in clinic. But we are looking at whether we can, based on just 3 days after infection or 5 days after infection, can we predict whether these patients will develop an organ failure in 1 month or 2 months' time, and which patients will have that, and how the patients could be helped, and how we could improve treatment so that doesn't occur. So who we are, so my group, so when me and John started, we were very small, but our group is growing. Our group is called CODI. It's the UCL Digital Health and Intelligence Collaborative, and it consists of computer scientists, clinicians, and also the human-computer interaction scientists, and nurses and patients. Patients are very much part of our clinical studies, and they are co-designing with us. So one of the really important projects in our group is actually working with patients and designing this medical technology for patients to really engage with, to uptake it, and to kind of flourish with it. Because right now, the patients are very reluctant to take medical technologies, and because they are not really designed with patients in mind. So we work together with Jeremy and one of the world-leading human-computer interaction scientists, Professor Ivana Drobnjak, who is just right here, if anybody later would like to discuss about HCI. And we designed a series of workshops in which we are really talking to patients. We are trying to understand the reality of their cancer journey. We are prioritizing key themes and needs, and hands-on prioritizing features via high-fidelity waveforms. In this process, we have discovered many different needs and emotions and ways in which the patients would like to use the technology. But one of the key emotions that we found was important for patients and key needs is the reassurance. So the patients really want to use the medical technology at home if they feel that that in some way makes them feel safer, that if in some way makes them worry less, that in some way it connects them to those clinicians in the hospital. And to design this and to create something like that is extremely hard. Myself, I mean, probably all of us kind of know a little bit about that. I used to wear an Apple Watch for a long, long time, but now I don't anymore. I used to, be on my screen all the time, but now I don't want anymore. The COVID has really changed something in us, and we sometimes do get tired from technology. So how do we design something that can look after patients, but that is still technology? And this is why human-computer interaction is fundamental. At this day and age, when the AI is developing so rapidly, where ChatGPT just took us all by surprise, I believe that the future, the key areas in the future in science will be the human-computer interaction. And it will be both beneficial for humans and for possibly that AI algorithm that one day might become aware. So in order for this whole research, both the computer science research and clinical research, to actually be able to make impact with that, what in those 3 years I found out essential was to connect with industry. Industry is essential because it can help us commercialize things and bring things on large scale to hospital and to patients. So in the lack of having an industry partner at that time, John and me and Pramit and my postdoc Ronnie, we created a UCL startup. And a startup, a company, little company called Ethera Health. And this company the goal of this company is to create a complete remote patient monitoring solution. And we were very lucky that in the first year of operating, we actually paired up with the GE Healthcare and to work on their Edison intelligence platform to bring in the remote patient monitoring element to it. And our project, called Halo Tract, is this prospective observational study to test the framework for integration of all different data streams, including molecular, genomic, biometric, imaging, and EMR data in patients receiving chemotherapy for advanced cancer. So you can see that in academic world, and being an academic, it is to do a lot with research, but it is also to do with so many other things. And for me, one of the most important and fundamental things, in addition to everything I spoke about, was really teaching. And throughout my career, ever since I was an undergraduate student, I was in some way, in some form involved with teaching. From private tutoring to being a lecturer to, and supervisor, I absolutely loved it. And it was always a way for me to connect with students and to new generations, and to myself as an academic, to get feedback from them and improve in the way I see the research and the university. So this also is very connected with my next admin, some would call, or management role that I got. Like I said, I usually choose to do admin that I feel passion for. So now I'm the director of the undergraduate program, which fully aligns with my love for teaching. So I'm fully invested. I chair the DSSCC committee, in which the students and the academics work together and making the department a better place for teaching. And some of my lovely students are here with us today. Thank you for coming. I actually initiated a programming tutor scheme, again with a student. A personal TUT, which over a few random chats, he said, our department could do with a programming tutor scheme, because the new students who come to the department, some of them just don't know how to program. So we designed a scheme in which is led by students, supported by academics. The senior undergraduate students are teaching the newly come undergraduate students how to program. And I'm very proud of the schemes. And students from that scheme are here with us today as well. So I wouldn't be able to do any of these things if I didn't have a really great team working with me. And my little mini DTC, these are a few of us in a little committee really trying and working really hard together with a much wider teaching and learning team, which is extremely large and very dedicated in our department. Finally, to any of you who are young students or academics, if you want to become an academic, one of the funnest things is to become part of the world kind of research, the wider world research community. There is so much fun and so much joy to be serving on those different committees around the world. It allows you to connect with other people, to see what they are doing, to connect with their lives, and it just makes the world like it's yours. Makes the whole world feel like it's your home. And I really, really love that, and I took every opportunity I had to become a chair of a diffusion study group, to be a chair of the diffusion workshop, to organize a conference. I love that. Being an academic is my calling. But to become one, like it is with a child, it takes a village to raise a child. It takes a whole small world to raise an academic. And this is a massive big world that I have to thank. And I really don't know where I would start. There's so many different faces here, and I think I've probably mentioned quite a few in my talk today. But it is to all my mentors, to my teachers, to my students, my friends, my colleagues, academic and non-academic. This to my family. I will just mention maybe 2 or 3 that I really simply cannot not do. The first one is Danny Alexander, my absolute academic role model, who never tried to be one. Danny is just academic, organically, naturally, does everything and doesn't need to learn or read a book. He taught me how to think critically, how to write. You should have just seen the first paper that came back from him. It was totally crossed out and read. Yes, and I can see some of the Danny group members laughing over there because, yes, Danny did make that kind of impact, not just on me, but on many other students and postdocs in his group. The second person I would like to say special thanks to is Heidi Johansenberg. She was the first female inspirational academic role model I met. If you knew Heidi, you would know how perfect she is. And anytime I needed support, even throughout my first maternity leave, I was really struggling breastfeeding, I would call Heidi for an advice. There were many other female academics, senior female academics, and male academics in my department. Yvonne, Anne, there are just too many. Thank you all. My family. First, I would like to thank I have to say this in Serbian, I apologize. Prvo, moj bati Seki. Hvala puno. Moj ljubavi. Moj mami i tati. Za vašu bezgraničnu ljubav i bezgraničnu podršku. Ceo život. Moj Vanji. Vanja, gracias para todos muchísimo. Es tu más familia también. Thank you to my little monkeys and to my little niece over there, Neva, who are the sources of my joy and my love. And the last, not the least, my husband, Richard, without whom nothing of this would be possible. My true partner in crime, who from checking my thesis many years ago, 15 years ago, sleeping on many different hospital floors, changing many a nappy, and helping me share this life in equal terms, encouraging me at every step to have a me time, to be myself, and who really checked through every major talk I'm talking, so including this one. Thank you. And thank you to all. I really hope that you enjoyed tonight, and I'll be very happy to chat to all of you after, during dinner and drinks. Thank you.
Wow. Thank you, Ivana. It's just an amazing journey. I don't know, I was thinking as I was watching it, it's so rare, actually, that you see your close colleagues speak at all, actually. I can't even remember the last time I saw you speak. But seeing the whole career laid out like that, I learned so much about you, even though I, see you day to day for the last however long it is, 15 years. Thanks for sharing all of that. I won't stand between you and the drinks for too long, but indulge me just with a few thoughts before we get there. I'm not even sure where to start, but as soon as Ivana joined my group back whenever it was, 2009, 2010, something like that. Thanks for the plug, Tim, by the way. I knew that this was not not a normal postdoc, and was going to have a transformative effect on the group, on my life to some extent, and then later on the centre and the department and the institution. And that relationship very rapidly, if it ever was a kind of supervisor postdoc relationship, I'm not sure it was, but it very quickly moved to one of colleague, ally, friend, in the kind of academic journey. And you've been one of the most important people in my career since then. More broadly, I think, as Steve said, Ivana's had a massive impact, not just on the research side, but in our department and institution, in all sorts of ways. I mean, force of nature, you know, determined, resilient, super smart, all the kind of academic things. But then beyond that, I think what really sets you apart is that kind of human touch. You know, as you said it yourself once in slightly different words, but I'll paraphrase. You know, you can, you have a passion for people and can make friends with anyone, doorman to dean, provost to postman. I forget what the student to, my alliteration is failing, but something else. And all of them get the same treatment, the same bandwidth, you know, the same beam of warm sunshine from you, and it's a massive quality that not many people share, and we're all very proud of you for that. What else was I going to say? So I had something else in my mind. It's gone. Never mind. We salute you, Ivana. We're so proud to see you reach the level of professor. I would sort of contest your analogy a bit. Have you reached the pinnacle of Mount Everest? I really hope you haven't, because I think there's going to be huge things in the future from you. At least I hope there are. I remember the other thing I was going to say, which is combining that sort of that human touch with somehow an immense capability for concentration. Whenever I see you at work, 95, probably 99% of the time, you're chattering with someone. I don't know who it is, the dean or the student or someone. And then outside of work, you have this huge family network of friends that I know you dedicate a huge amount of time to. But somewhere there's a time warp that you manage to find and go into to exercise this concentration and produce these, like the huge wealth of research we've seen and these massive tasks. A huge champion of women in science, and more recently, I think you're gradually revolutionising the undergraduate teaching here at UCL, and it's just amazing to see. I don't really know how you do it, but it's incredibly impressive. So everyone, please join me once more in thanking Ivana, both for tonight and for the career previously and what's to come. Thank you.
Thank you.